Hi and welcome to this video where I'm going to be looking at how we measure the brightness of night sky objects. We're going to figure out how you can measure the faintest objects that you and your telescope can see, and we're going to learn why that's a really helpful piece of information for you in your backyard astronomy. So let's jump in. Magnitude is the name of the scale that we give to brightness for night sky objects. Now there are two types of magnitude. There is apparent and absolute. Absolute magnitude is a measure that scientists use. It says if I'm a certain distance away from an object, how bright is that object compared to this other object over here when I'm the same distance away from that. Now that's not a particularly useful measure for a backyard astronomer. Instead we use apparent magnitude. And that is the brightness of an object as we see it standing down here on the surface of the Earth. The concept of magnitude is really old. It's about 2,000 years old and was developed by ancient astronomers who wanted to categorise the stars that they could see into different levels of brightness. And they opted for 6 different categories, with 1 being the brightest and 6 being the faintest. Today the magnitude scale has much more rigour, as you'd expect. And from a scientific perspective, we still have magnitude 1 and magnitude 6, but we've defined these much more clearly and said that magnitude 6 is exactly 100 times brighter than magnitude 1. Now the magnitude scale itself is what's known as a logarithmic scale, so it's not a straight line measurement. A magnitude 6 object, as we've just said, is not 5 times brighter than a magnitude 1 object, it's 100 times brighter. Which means an object that is 10 points along the magnitude scale is actually 10,000 times brighter than the object at magnitude 1. And the way to work it out for yourself is that each point on the magnitude scale is about 2.5 times brighter than the one before. So a magnitude 2 is 2.5 times brighter than a magnitude 1, and then a magnitude 3 is 2.5 times brighter than magnitude 2, which is also 2.5 times brighter than magnitude 1. Now if you do that 5 times, 2.5, 2.5, 2.5, 2.5, 2.5, that gets you to 100 times, and that's the difference between magnitudes 1 and 6. The magnitude scale we use today also extends in both directions. It goes below 1 and it goes above 6. On the brighter end, for example, we have Sirius, which is the brightest star in the night sky, and that shines at magnitude minus 1.4, i.e. it's so bright it's below magnitude 0. And then we have the bright planets. So Venus is the brightest planet in our sky, and that shines at magnitude minus 4.6 at its brightest. And then we have the full moon, which can shine as brightly as magnitude minus 12.5, 12.6, somewhere around there. Now the difference between Venus and the moon, as I've just described them, is about 8 points on the magnitude scale. But as I've also just described, each one of those is logarithmic, so it's 2.5, 2.5, 2.5. And what that actually means is the difference between the moon and Venus is about 1,500 times, i.e. the moon is about 1,500 times brighter than Venus, even though there's only 8 points difference between them on the magnitude scale. Now on the other end of the scale, beyond magnitude 6, which is about the limit for what we can see with the naked eye under a dark sky, we have the billions upon billions of fainter objects. So we've got fainter stars, we've got gas clouds, nebulae, we've got galaxies in their billions as well, all of which are beyond magnitude 6 and not available for us to see with the naked eye. Now of course our telescopes can pick those up and they can see beyond magnitude 6. In general terms, a backyard telescope can see somewhere between magnitude 12 and magnitude 14, depending on the quality of your seeing, how dark your sky is, and most importantly, the size of your telescope. And nothing says that more clearly than when we look at the Hubble Space Telescope, for example. That massive mirror flying around in space with no atmosphere and no sunlight to get in the way can actually see objects as faint as magnitude 30 or 31. Several billion times fainter than anything we can see from a backyard telescope. And the James Webb telescope, well, that can go even further, potentially limitless in the magnitude it can see. The limiting factor for the James Webb telescope is actually the amount of time a scientist can point it in one direction to gather enough light in to see those really faint objects. Let's bring that back to Earth. How is magnitude useful for us as backyard astronomers, and what can we use it for to improve our astronomy? Well, there are two sides to that coin. One is we can use it to work out what we can see with the naked eye from our observing location, and the second is we can use it to work out what we can see through our telescope. The magnitude measurement that we can see with our telescopes is the theoretical maximum, so we'll need to temper that with our experience and the effects of the atmosphere and light pollution. But it's still a useful number to have at our disposal nevertheless. And when we know these limits, whether it's our naked eye limit or the telescope limit, we're able to understand which objects we can look for. So if they're too faint for our telescope, we know there's no point in trying to find them because they're just not going to be visible to us. And we also know that if we can only see stars to magnitude 5 and we've got a star map that shows stars to magnitude 6, we effectively just need to ignore the faintest stars on that star chart when we're holding it up and looking for directions in the night sky. So how do we work out what our limiting magnitude is, our naked eye limiting magnitude is, i.e. how do we discover what's the faintest stars that we can see with the naked eye? Now, one of the simplest ways of doing that is to use the asterism known as the Great Square of Pegasus. This is, unsurprisingly, in the constellation of Pegasus and is marked by 4 bright stars in the corner that we can see from practically anywhere on the surface of Earth, even under fairly significant light pollution. However, inside the square itself are a number of stars that range from about magnitude 4.5 all the way to sort of 6.4, 6.5, which is the absolute limit of what the naked eye could see if there was no light pollution at all. And when you observe the Great Square for yourself, the number of stars that you can see within that square tells you what the limit is that you can see from your location. Now, if you can only see one star within the square, that's Upsilon Pegasi, that shines at magnitude 4.5, and basically that's your naked eye limiting magnitude. However, if you can count 4 stars within the square, then your limiting magnitude is about 5. If you're lucky enough to spy 7 stars, then you're about magnitude 5.5. And if you're fortunate enough to see 10 or even more stars, then you're probably just about at the limit of what we can see with the naked eye anyway. So 10 stars counted within the Great Square means you've got visibility down to about magnitude 6, which is as good as any of us can expect. One watch out for using this, though, is to make sure that, one, the Great Square of Pegasus is quite high in the sky. What we don't want is for atmospheric thickness to be clouding some of the stars that you can see. So the higher up, the clearer the air. And the second thing is you need to make sure your eyes are dark adjusted. So it's no good stepping outside within a few minutes doing this test. Make sure you've been out there for a while, good 20 minutes, so that you're getting a true measure of the faintest stars that you can see with the naked eye. So that covers what we can see without any equipment, but the most important thing next to do is to work out what we can see with our telescope. So what are the faintest objects that our telescopes can deliver to us? And one of the best ways of doing that is with an online calculator. Now, the one I use can be found at cruxis.com/scope/limitingmagnitude.htm, and I'll put that link below so you can use it for yourself. Click over to that site and place in there the information that it asks for. So specifically, the aperture of your telescope is very important, what type of telescope it is, and some additional bits of information which aren't massively important, so don't spend too long trying to work out what the perfect answer is, because the main impact basically is what kind of telescope you have and how big its aperture is. Feed all the information into the table that it asks for. Do your best guess if you're not entirely sure what the perfect answer is for one of the questions. Click calculate, and that will tell you what your telescope's limiting magnitude is. Now, you've got 2 really useful numbers when you've done all that, and they're both related to magnitude and they're both related to the brightness of the objects we can see. As I said at the beginning, with the first one, that naked eye limiting magnitude, that tells you what you can expect to see of the heavens or how you can explore the stars just using your naked eye in the conditions that you have locally. taking account of the light pollution that you are under. The second measurement is perhaps the more useful one. It's the one for your telescope and says these are the faintest objects we can see. So if it's coming out at 12, 13, I personally would knock that down a bit so you don't get too disappointed hunting for things right on that edge. Basically means that objects at magnitude 9, magnitude 10, magnitude 11 are perfectly within scope, if you pardon the pun, for you to find. As you get more experience at hunting and using averted vision and things like that, then by all means push your telescope to those limits of 11, 12 and 13. And with the naked eye limiting magnitude, you also know how useful a star map is for you. Like I said earlier, if it's got magnitude 6 stars on it, but you know you can't see beyond magnitude 5, then you can adjust your expectations accordingly. And in another video, I'm looking at how to use this information to indeed read star charts. So that's it for this video. Why not get outside this evening if the skies are clear, and see if you can find the Great Square of Pegasus and do that assessment. How dark is your sky? What are the faintest stars that you can see? And there's no reason why right now you can't click across to that website, enter your telescope information and work out what are the objects that you should be looking for. I hope you found this useful. I hope you have great fun, and I wish you, of course, clear skies.